Well, for those of you who are watching this tape, it's probably sunny and very pleasant in Livermore. I'm in the middle of Siberia now, eating borscht and pickled bear's heads or something. So I'm probably having a better time than me. The title of this talk is, Can Micro-Thermonuclear Fusion Occur in a Sonoluminescing Bubble? This was not really the original title of this talk. Originally, this was absent. Classification got hold of this, and they had collectively had puppies over this because they didn't want this word by itself in this talk. So we began an intense period of negotiation where they were saying, well, we'll have femto, atto. I finally got them up to micro, but they wouldn't go any bigger than micro. My collaborators are Doug Clark, John White, and Dave Young. They've been working with me on this project for the past 5 years. I want to make a comment about the funding. The sonoluminescence research at this lab has been supported by the Defense and Nuclear Technologies Directorate through the containment program. And I want to make a special plug for Norm Burkhardt. If it hadn't been for his support during this, these 5 years, none of this research would ever have happened. Well, let me skip to the end first. We believe that tabletop fusion may be possible, but we haven't yet measured any thermonuclear neutrons. However, some people believe more than others that it's possible. This appeared in the London Independent, November 3rd, 1995. Iraq could foil a nuclear test ban by using sonoluminescence to simulate nuclear weapons. My personal feeling on this is that if the Iraqis want to spend their entire defense budget, a military budget, on sonoluminescence, the world will be a much safer place. Okay, this is the outline of the talk. First, I'll describe what sonoluminescence is. Then I'll talk about the surprising observation that caused all the flurry of research, a plausible explanation, shock waves, and then some of the numerical simulations that we've done for a gas bubble in water, and then some comparisons with experiment, and then finally I'll get to micro-thermonuclear fusion and discuss what's needed. Well, first of all, what's sonoluminescence? It's the conversion of acoustical energy to optical energy. The way it works typically is you have a flask. The flask is filled with a degassed liquid, and there are transducers around the outside. These transducers oscillate at the resonant frequency of the system, so that's determined by the liquid and the size of the system. For something like this that's about 3 centimeters in radius, you have 27 kilohertz. While the transducers are oscillating, they set up a standing wave inside the flask. If you inject air with a hypodermic, or if you boil a little bit of liquid, a bubble is created, and it's trapped at the center. And what it does is, in phase with the acoustic drive, which is a sinusoid, just back and forth, the bubble expands and then collapses. When the pressure is negative, the bubble grows, you get collapse, and at the conclusion of the collapse, you get light. There are two kinds of sonoluminescence. There's single bubble and multiple bubble. And I'll be discussing primarily single bubble in this. So there's only one glowing bubble in here as opposed to many. And I'll talk a little bit about some of the differences. Well, let me give you a little bit of history. Sonoluminescence was discovered in 1933 by Marinesco and Triat. These were some inpatient photographers, I guess. They had their photographic plates in a bath, and they decided they wanted to try and speed up the developing process. So they threw an ultrasound head in and jostled it. They got all these bubbles all over the place. And when they looked at their plate, they saw it was completely exposed, all speckled. And what was determined was it was light. Bubbles were being nucleated, collapsing, and glowing and exposing the plate. And so this is when it was discovered. In '59, Meyer and Kutroff found that the light flashes were periodic. That is, with the driving amplitude, the sinusoidal driving amplitude, they found that the bubbles actually grow and collapse in phase. And they did this by using a nickel rod and slowly growing a bubble and watching sonoluminescence off this, the end of this nickel rod. In general, it's been assumed that the optical emission is due to heat in the collapsing bubble. But the exact mechanism has never been clear. And in general, the temporal studies were too slow, 1 per microsecond. No one ever dreamed that you need 6 orders of magnitude faster resolution in order to see what's going on. Then in 1990, Felipe Gaitan, a graduate student at National Center for Physical Acoustics, managed to get his thesis advisor to sign his thesis. This was his tremendous accomplishment. The fact that he did it by levitating a single bubble is only secondary, but it was very interesting. He achieved stable sonoluminescence. His original PhD was to study multiple sonoluminescence, and he insisted, how can I do physics on lots of bubbles? I need to isolate one. And it had never been done, and since he didn't know it couldn't be done, he didn't see why he couldn't go ahead and try doing it. So he did that. His thesis advisor kicked and screamed until he did it, and then his thesis advisor patted him on the back and said, this is fantastic. This set the stage for a very surprising observation. And that surprising observation was by Barber and Putterman, who used Gaetan's scheme of the stable sonoluminescence, that is just one little single bubble suspended in here, to make some measurements. Well, everyone saw that there was blue light to the unaided eye. Gaetan saw that. But Putterman did some spectral measurements and some temporal measurements, and he found that the temperature of that little bubble, a glowing bubble, was very hot, about 2 volts. It's about 20,000 degrees. That was the best estimate based on spectral analysis at the time. The most remarkable measurement was the pulse width. That is, a flash is emitted with a duration of about 50 picoseconds. Now, this is amazing because these transducers are driving the system with a period of about 30 microseconds. So how do you get this incredible change in time scale? At the time, no existing model could explain the 50 picosecond pulse width. When Putterman published some of his results in the Wall Street Journal, he had talked about a failure of Navier-Stokes. F doesn't equal ma. Newton's laws are violated. Well, this was absurd. Maybe it was a cooperative phenomena, laser, superfluorescence. The acoustics community didn't have a clue as to what was going on because this was so far outside the regime of normal acoustics, they just didn't know what to make of it. Now, if you haven't seen it, this is a picture. If I cover this up, I could tell you that this is the NOVA target chamber, and these are the laser ports. If I show you the 500 mils, you'd guess that no, it's not. So this shows the bubble suspended in the center of the flask. There's an interesting story about this picture. When it came back from the photographer was very upset. So he said, there was this darn spot in the center, and we had to airbrush it out. So he said, no, you can't. That's the data. We need that. Give you a little bit of theoretical history. The previous theoretical analyses of the collapsing bubbles can't explain the recent experimental data. In 17, it began, as one might expect, with Rayleigh, who looked at an incompressible liquid in a void and did a nice, very elegant theoretical analysis and came up with millisecond-type collapse times. In 1950, Nolting and Neperis took Rayleigh's analysis through an ideal gas in the center, a little viscosity, a little surface tension, and said the bubble collapses and it gets hot. And there were some after bounces. Trilling tried to do a compressible analysis, much like our modern hydrocode analysis, and he did a partially compressible liquid, an ideal gas, and followed the compression. And he found that there were no shocks. It was a totally isentropic compression. If he had gone a little further, he would have seen the shocks develop. He missed it. In 1960, Jarman, in a short paper, suggested, without analysis, that, well, there must be shocks. That is, as the bubble collapses, there must be a shock that's whacking into the center of it. Between then and the present, most of the work, I guess, has been done by Prosperetti. He did a lot of work using the Nolting-Neperis model and adding thermal conduction and other details and cleaning up some fine points. And found in general he could get pretty good agreement with the experiment. That is, if you look at the bubble as it collapses, and then there are some after bounces. And the frequency and amplitude of these after bounces is dependent on some of these features, and Prosperetti had mapped that out. Except the one thing that he had no handle on and all the models break down at is for the main collapse that gives you the flash, which is the interesting physics. In '93, Wu and Roberts did the first published hydrodynamic simulation. The shortcomings with that model, that analysis, was that they had a simplistic air model and used a Nolting-Neperis type analysis for the water. And so the water equation of state or description wasn't valid. The air equation of state wasn't really valid. And so their general results were called into question, especially since they got central temperatures on the order of 100 million degrees, which is absurd. Well, recently, Hollywood has made the biggest advances in sonoluminescence technology. However, there still is no explanation of the origin of the 50 picosecond pulse width or spectra. Keanu just wouldn't let us know how he did it. Well, how did I get involved in this? About 5 years ago, I was on my way to the test site working on another project. And very often, my wife sticks things in my bag, gives me things to do. And she had found the article in Science Magazine almost 5 years ago to the day to describe Putterman's measurements, and in particular this 50 picosecond pulse width, and the fact that Newton's laws were violated. Well, my wife's a biologist, and even she knew that this was kind of peculiar, so she circled this and said, F not equal to MA, question mark, big red magic marker. You better look at this. And so that's how I got involved in this work. If it hadn't been for her, I wouldn't have done the work. Well, it was a fortunate set of circumstances. My wife gave me the article, and I happened to work at Livermore. And at Livermore, we have a very simple view of all physical phenomena. All natural phenomena are either an implosion or an explosion. And so naturally, that had to be the explanation of what was going on with the bubble. Right? Give a child a hammer and everything becomes a nail. So we have a simple implosion and explosion. Something heats the gas rapidly, initiating optical emission, and then something follows immediately to quench the emission. So we hypothesized rapid heating by spherically convergent flow, shock waves, and then rapid cooling by spherically divergent flow, and then thermal conduction. The big question was, could this occur fast enough to be consistent with the measured 50 picosecond pulse width? Up to the time that we began our studies, full hydrodynamic details of late-time collapse had never been studied. And by that I mean a nonlinearly compressible water, high pressure and temperature gas equation of state, plasma and radiation physics, consistent boundary conditions, all the things that we do here as a matter of course. Well, I've talked a lot about shock waves, and let me explain how shock waves are involved with the collapse of the bubble. A shock is a moving discontinuity that evolves from a steepening pressure wave. So let's consider a cylinder filled with gas and a piston that moves. As the piston moves, a pressure wave is sent into the gas. It is the property of all materials that the sound velocity is higher when they're at higher pressure. Well, what does this do? It means that this part of the wave is going to move faster than this part because this is at higher pressure. And so this is going to catch up. And so it steepens and eventually forms a shock. For any piston velocity, it doesn't matter. If it's a very low velocity, it'll just take a long time to form a shock. If it's a very fast, high velocity, it'll form quickly. Now, how does this relate to the bubble? The bubble is gas surrounded by liquid. Here's the gas, and the gas-liquid interface acts as the piston, driving the shock into the system. The basic assumptions in our model are very simple. Compression heats the bubble. Hot matter emits light. If you've ever taken a foot pump and pumped up a bicycle tire or a car tire, you step on the pump, and the pump gets hot. Why? Compression heating. And that's what happens here. There's been a lot of talk lately about quantum vacuum fluctuations giving rise to sonoluminescence, that there are 13, not 14, not 12, but 13 jets that form when the bubble collapses, and they hit each other, and light forms the same way light forms when you take a wintergreen candy and crack it in your mouth. This is reaching a little bit. You squeeze the bubble, it gets hot and it glows. That's what we think happens. So what are the experimental observables that we're going to be trying to simulate? A pulse width less than 50 picoseconds, and a visible spectrum that looks something like a 2 eV blackbody radiator. If we look at the energy that's emitted, the emitted light, and we compare it to how much energy is in the compressed bubble, just to get a feeling for the order of magnitude of the energy that's emitted, we're down by 5 orders of magnitude. Well, what does that mean in terms that you can better grasp? It means if you take the energy of the emitted light, it'll heat 1 teaspoon of water 1 nanokelvin. There is not very much energy coming out per flash. But it also means, because of that, that the details of the flow of energy from the large energy reservoir, which is this hot compressed gas, to the small energy reservoir, which is the emitted light, is important. That coupling is important. Small errors could lead to large errors in predictions of the amount of light. So let's continue a little bit more with the basic model. Compression heats the bubble. Hot matter emits light, and it does it by an energy cascade. So if we begin with our glowing bubble, during the collapse, it's heated by a shock. the contents ionize partially. So you have ions and you have electrons. The shock energy goes into the ions. They have most of the mass, they get most of the energy. There's also PDV work that's done on the ions, pressure compression. The ions then lose energy by conduction. They also lose energy by coupling to the electrons. The electrons gain energy by this PDV compression. It's just being squeezed, so the electrons also get hot. The electrons lose energy by conduction, and they also create light. This is where the light comes from. The temperatures are not very high. They're very low. And this creates a bit of a dilemma, because we're really too hot for cold physics, and we're too cold for hot physics. We're in this never-never land that is not well understood theoretically or experimentally. This just happens to be where sonoluminescence lives. However, all is not lost. The short collision times between the ions and ions, the electrons and the electrons, and the ions and electrons, and the very small amount of energy that is in the photon field, the light field, simplifies greatly the calculation of the emitted light. And I won't go into that. I'll just say that it's a state of local thermodynamic equilibrium that's set up, and that makes the calculation of the emitted light much simpler than it otherwise would be. Still not simple, but much simpler. Well, how do we go about simulating the collapse? We discretize in difference the hydrodynamic equations of motion. Basically, you can write equations that say mass is conserved, momentum is conserved, energy is conserved. And you can take the gas and the liquid, divide it up into little regions, each region having a fixed amount of mass, but the mass can differ from zone to zone. And you enforce the conditions of the hydrodynamic equations, that you conserve all these quantities, you apply a pressure wave, or the driving force, and then you just follow the waves as they go through. And this is a standard way that our hydrocodes work here. We solve these equations incrementally in time, and we only look at one of the many growth and collapse cycles, where the experiment works at 30 kilohertz, so that's 30,000 per second. We're only looking at one particular collapse. And for typical parameters, the R naught is 4.5 microns. That's this size of the ambient bubble. The flask is 3 centimeters in radius, driving 27 kilohertz with a driving pressure, overpressure of 0.23 bars. When you put this in, you typically get 45 microns maximum radius, and this is typically what you get experimentally, this 10-to-1 expansion ratio. Now, why can we get away with just doing one cycle as opposed to many? Well, the implosion is driven inertially, and so any set of parameters that gives a radius of time, that is the motion of this boundary, that's consistent with experiment, should supply the sufficient energy to power the system and give us and generate the necessary inertial forces that generate the flash. So if we put all that together, what do we get? This shows the radius versus time of that little bubble. Remember that we start with a negative phase of pressure, so we're pulling on the flask a little bit before we push. And we pull, that wave has to move through the flask, through the liquid, to get to the bubble. So the bubble is sitting there, everything is at rest in equilibrium. So nothing happens until that wave reaches the bubble, and then the bubble begins to grow. And that's what's shown here. And then it collapses. It goes supersonic about this point, 2 microns or so in radius. And Mach 1 is when you talk about Mach numbers, it's really a squirrely thing, because a Mach number is a ratio of a velocity to a sound speed. And depending upon what sound speed you choose, you can have a Mach number be anything. So the Mach number that we're using here is defined as the ratio of the velocity of the interface to the speed of sound in the gas just right in front of the interface. And that's a reasonable Mach number definition to use for describing the formation of shocks. We're interested in the final little area right down in here. There's a very interesting feature of this collapse. This is a gentle growth and collapse. It's isentropic until the final 10 nanoseconds. We have 30 microseconds here, but until the final 10 nanoseconds, it's isentropic. This is a kind of implosion the laser fusion people would kill for. Of course, they're driving it hard to get a lot of energy out. We're not driving this hard, and so that's why I guess we have these conditions. But there might be interesting things one can learn from a detailed analysis of stability and collapse of these bubbles that might be useful for ICF. Okay, well, what do we get? This shows the results of a typical calculation. Now, I'll go through it slowly. This shows the radius versus time for the final 80 picoseconds of the collapse, 80 picoseconds. And this shows emitted power. Well, first let's start with this. This is the bubble radius as a function of time. Remember, we started at 4.5, it grew to 45, and it started to come in and come in. This, we pick it up here when it's at 0.36 microns. It comes in. Now, we talked about the shock wave. As the bubble collapses, we said that it pushes the shock wave through. So the bubble is still collapsing, the shock wave is racing ahead, right over here, hits the center, bounces back, bubble's still collapsing, and then the shock wave hits and then turns the bubble interface around. When the shock wave comes in, it heats and energizes the system and causes light to be emitted. This is a calculation of the emitted light, both these curves. As the shock runs out, there's a divergent shock wave. The material expands, it cools, and the light emission is terminated. We see two conditions here that we've calculated. And this shows why the plasma thermal conduction is important. If we do not allow plasma thermal conduction, that is, we don't allow the electrons to remove energy, we find there's a very long tail and the pulse doesn't turn on and off. It's not a short pulse. If we allow the conduction, which is primarily by the electrons, we see that we get a very narrow pulse, and this is consistent with experiments. So we think that we have isolated the origin of the picosecond pulse and the key physics that determines why we get the pulse width the way we do. It's basically the rapid rise of temperature due to the shock, then the rapid drop of temperature due to the subsequent expansion, which just turns off the emission. Now, there's an interesting feature. You might ask, well, what does this look like if you were to look from the outside? When you look at the sun, you see it's yellow and this apparent surface temperature of, 7,000, 8,000 degrees. But you know that it's 100 million degrees in the center. You can't see all the way through it. It's optically thick, for a good part of the way. The same thing happens in this bubble. This shows the region of optical thickness. So imagine you're looking into the bubble now spatially, so you can see all the way to the center. As soon as it gets energized and there's light output, you can't see beyond here. So what it looks like is this. You can see through this fuzzy halo, but you can't see the center. And the emission properties are based on this fuzzy halo and the surface of this thick region. The energy that we calculate from this, about 0.15 MeV per flash, and it's about 33,000 photons coming out per flash. And this is for nitrogen. Well, that's one piece of data that we need, that any model has to be able to predict. You have to be able to explain where these pulse widths come from. The next thing you have to do is get a little more quantitative. That is, can you explain the spectral output? We find that our calculated spectra are consistent with the experimental spectra. The experimental spectrum for nitrogen, that's pure nitrogen, is about 1/25th as intense as the air spectrum. You might say, well, gee, air is mostly nitrogen. Well, it turns out the other trace components in air seem to make a big difference. When we calculate the nitrogen spectrum, then the previous slide, if I calculate the spectrum from that calculation, I get this blue line. The units are femtojoules per nanometer versus wavelength in nanometer. And I get this calculated spectrum. If I multiply it by 25, it lays pretty close to these dots. These dots are the experimental air data. So it means that calculationally, it looks like we understand the nitrogen spectrum. Well, what about air? Recently, LOSA in Germany made an interesting, put forth an interesting proposition. He said, suppose when the bubble gets hot, there are chemical reactions that occur. So the nitrogen and oxygen are cooked off, and all you have left is the chemically inert argon. This would mean that the bubble is primarily argon. Now keep in mind, when a sonoluminescent air bubble turns on, it doesn't turn on right away. The bubble gets trapped, you turn up the intensity, and there's a short period until it begins glowing. So LOSA said that's the chemical time where reactions are occurring, and after that you have pretty much an argon bubble in there. We did a calculation replacing the gas inside with pure argon. And this is the spectrum that we calculated. It agrees very nicely with the air data. This is very strong evidence that Los is right and that a sonoluminescing air bubble is actually a sonoluminescing argon bubble. Well, what does all this have to do with microthermonuclear fusion? In order for me to talk about thermonuclear fusion in a tabletop device, which most people might say is impossible, I have to establish a little bit of credibility. The agreement of the calculations with the experiments gives me that predictive capability, and it gives me credibility. It says I can calculate something that people can measure. Now, we know that the calculated temperatures at the center of the bubble can be high. However, thermonuclear fusion temperatures requires temperatures that are much higher. The reactions that we're looking for are DD reactions, proton and neutron with a proton and neutron, producing helium-3 plus a neutron. With the neutron has 2.5 MeV of the 3.2 MeV. So this is what we're looking for, the kind of thermonuclear reaction. So how do we do this calculationally? Well, we replace the air with deuterium gas. We replace the water with heavy water, so that all the species that are involved in the system are the thermonuclear fuel. When we do this, we calculate temperatures that are only 20 volts, far too low for fusion. And the reason for this is interesting. It turns out hydrogen, deuterium, is extremely squishy. So when it goes to compress, all the energy goes into compressing it, and you can't get it hot. It's much squishier than nitrogen. So we conclude that you can get no fusion from a standard sonoluminescing deuterium bubble.
You do get light.
Oh, you do get light, yes. So what do you do? Well, what's the best way to achieve fusion from this system? This is a complicated system, and it's a finicky system. What can be modified? We can play with the flask, the size, the thickness, the material, acoustic impedances, change the driving liquid, low density, maybe high density, gas composition, bubble size. Do we want lower sound speeds, bigger radius, ambient temperature, pressure, driving pressure, amplitude, frequency, structure? There are loads of things to change. I chose a practical approach, might even be considered to be chickening out, is to just minimize the perturbations to a standard sonoluminescing system. If I'm going to do theoretical calculations and come up with a method for tabletop fusion, it has to be something that an experimentalist can implement easily, or they're going to throw me out of the laboratory. They're going to say, go away. So what did we come up with? Came up with the idea of a spiked driver. Remember, the normal drive is this oscillating, it's a sinusoid that's applied to the outside of the system. That sinusoid sets up the standing waves in the flask, and it also powers the collapse of the bubble. So we said, well, let's split the duties. Let's use the sinusoid to set up the wonderful conditions of resonance that allow sonoluminescence to occur, but let's put a spike on. So as the bubble collapses, this well-timed spike gets there and enhances the collapse. We don't want to upset the gross system acoustics, and we suggest to supply a well-timed kick. There's qualitative evidence that this works, but nothing quantitative to date. And that's because the work has not been done. It's not because we've looked for it and didn't find it. It's an important point. There are issues of funding. So I'll say once again, the agreement of the calculations and the experimental data lends credibility to the thermonuclear fusion estimates. So let's put it together. We have the spike drive, and remember we have the ions and electrons coupling. We said you get ions and electrons, and what's important is that it takes time for the ions to transfer their energy to the electrons. That time is important because fusion comes from the ion-ion collisions. So what happens is during the collapse, for a brief instant, fraction of a picosecond, the ions get very hot. The electrons don't. This is when the fusion can occur. The fusion rate in this regime is very sensitive to the ion temperature, goes like the fifth power, and the density. So any little tweaks can make a big effect on the fusion yield. Now, what is this big fusion yield? About a neutron per hour. Now, how big is this? Well, again, let's put it in terms that are easy to understand. Suppose I evict the population of the world, and I cover the world with these machines, about a square meter apiece. I let these machines run for an hour, and I gather all the energy produced by these machines, all the thermonuclear energy. I would have enough energy to heat a cup of water 1 degree. So we don't have a competitor for NIF here. This is not going to work that way. On the other hand, for $1,000 worth of equipment, this is a measurable number, and you can demonstrate tabletop thermonuclear fusion, which has never been done. So it's still very interesting, as well as the physics that goes along with it, because this is interesting for many applications, the fact that you do get temperatures this high and the separations. So there's a tremendous amount of interesting physics that's going on. So, summarize. We've simulated the collapse of a gas-filled bubble. We found that shock waves are generated during the collapse. The gas near the bubble center is heated and begins to radiate light. The shock rebounds from the center as an outward expanding shock. The cooling from thermal conduction and expansion then stops the light emission. So this, in a nutshell, is what's happening, why it happens, and how it happens. We find that our calculations agree with experimental data. Now, there are a lot of things I didn't talk about. The pulse width I mentioned, spectra I mentioned. There's also the amplitude of the shock in the liquid when the outgoing shock passes out and goes into the liquid. And we have calculated that and measured that, and there seems to be consistency. So there's another reason for believing that we may be on the right track. I mentioned there is no afterglow. You might expect a hot bubble. After this flash occurs, it's still hot. You might expect there's still to be more emission as the bubble expands and cools. It turns out that's not the case because of the details of the emission physics that I can't go into. But we have found that there is no afterglow. This is a prediction that we've made, and to date, some people have looked and they haven't seen any afterglow. So there's just one flash, and that's it. We've explained the difference between noble and diatomic emission. Noble gases are much brighter than diatomics, and we've explained that, although I didn't explain it in this talk. Also, the sensitivity of the emission to bubble dynamics. If you have a bubble that begins at a certain size, R0, and goes to R max, if it goes a little bit bigger, there's an incredibly strong sensitivity to the light output. And this has a tremendous bearing on all of the experimental data that's been published to date and trying to compare one experiment with another. You need to know what the bubble is doing in order to know how its output compares to another experiment. You need to know what those radii are. And I also want to point out that our results are far beyond the predictive capabilities of any other model anywhere. And finally, we conclude that micro-thermonuclear fusion from a deuterium heavy water system may not be impossible if the collapse is enhanced. Thank you very much.